Hello everyone, welcome back to my video Pure Bending. So in the previous video we have analyzed the stress and strain of the homogeneous beam subjected to coupled force or bending moment. So in this video we will further analyze the stress and strain of the composite beam. Okay, composite beam. So let's start with what is the definition of composite beam. So composite beam is the beam that is constructed by two or more different materials. Okay, for example, if we have a beam, that is made from only single material, which is material 1, and then subjected to bending moment M. So this is what we call as a homogeneous beam. Okay, homogeneous beam. Now let's say the beam is made from two different material. Okay, two material or more. Okay, for this case the beam is made from material 1 and also material 2. Okay, and then subjected to bending moment M. Okay, bending moment M. So this is what we call as a composite beam. Okay, so this is what we call as a composite beam. Okay, all right, because the beam is made from two material, which is material 1 and also material 2. Okay, now to apply the fractional formula for composite beam, we have to modify or transform the composite beam into equivalent single material beam. Okay, so before that, let's look at here this second point. Fractional formula was developed assuming the member is made from homogeneous material, single material. So the fractional formula, which is sigma equal to my over I, that previously been derived, is assumed that the material is made from homogeneous material. So if the beam is made from more than two material or two or more material, so we cannot straight away apply this formula. Okay, so what we have to do is we have to transform, okay, the composite beam into equivalent single beam. Okay, so if we have for example this beam, okay, this is a front view. So if we look at from the side view, so we can see, okay, this is the same beam, this beam and also this one, but this one from the side view. Okay, so that will be the material 1 and that will be the material 2. Okay, so what we have to do is, in order to apply the fractional formula, okay, for this type of beam, we have to transform the material, okay, one material to another. Okay, for example, we transform material 2 into material 1 or material 1 into material 2. Okay, so after transformation, so the composite beam can be treated as a homogeneous beam. So in order to do the transformation of the beam, what we have to do is the width, okay, of the material that intended to be transformed must be multiplied by the transformation factor n. So how to do that? So I will explain in detail in the next slide. Okay. Okay, now let's look at on how the stress and strain distribution, okay, in the composite beam. Okay, composite beam. Okay, now let's say we have composite beam which is made from material 1, which is material 1, and also material 2. Okay, so because the material 1 and material 2 is firmly bonded, okay, bonded each other, so when the beam is subjected to bending moment, so what happens if the beam will deform uniformly. Okay, will deform uniformly. For example, we have composite beam, which is the beam is made from material 1 and material 2, and then subjected to bending moment M. Okay, so after deformation, what happened? The beam will deform uniformly. Okay, uniformly. Okay, so what does it mean? So it means that the strain distribution, okay, the strain distribution will be also uniform. Okay, so it means that the strain distribution, okay, is uniform. Okay, so that's why we get picture B. Okay, picture B. So the strain is uniformly distributed in the beam, or varies linearly. Okay, with respect to the y. Okay, with respect to the distance y. So we can write that the strain, okay, the strain at x direction, because this is the x, okay, because this is the x. So the strain at x equal to y over rho. Okay, so this has been derived. Okay, has been derived in the previous slide. Okay, in the previous slide of previous video. Okay, so if we replace, if we replace or we expand, okay, expand the equation for the stress is equal to stress 1, stress material 1. Okay, let's say the stress material 1, okay, must be equal to the E1 strain. Okay, this is based on the Hooke law. Okay, Hooke law. Okay, so the stress equal to E1 Young modulus time by epsilon x. Okay, and then if we replace the epsilon x by y over rho, so we get sigma 1 equal to minus E1 y over rho. Okay, and also same thing for stress in material 2, which is sigma 2 equal to E2 epsilon x. Okay, so the value of the strain will be the same for both material, because the material is bonded together. Okay, firmly bonded together. And then same thing here, sigma 2 can be write as a minus E2y over rho. Okay, alright, so because the value of E1 and also E2 are different for both material, so that's why we will have the piecewise linear normal stress distribution. Okay, because the stress 1 and stress 2, okay, is varies linearly, okay, but having different slope. Okay, slope is represented by E1 and E2. So this is how the stress distribution in the composite beam looks like. Okay, alright, so this slope will be different with this slope, okay, because of the different value of Young modulus, okay, or modulus of elasticity. Okay, in order to simplify the analysis and straight away using the flexural formula, so what we have to do is we have to transform, okay, the composite, okay, composite beam into homogeneous beam. Okay, so this is to simplify the analysis. So what we have to do is we transform the material 2 into material 1. Okay, or we also can transform from material 1 into material 2. But for this case, let's say we transform 1 into material 2 into 1. So this is how the beam will look like. Okay, so what we have to do is we have to multiply the width, okay, with B of material 2 must be multiplied by n. Okay, must be multiplied by n, and n is the transformation factor. Okay, so that's why you can see here, after the transformation, okay, after the transformation, the width of material 2 will be different. Okay, so if the material 2 having higher modulus of elasticity compared to material 1, and then the width or the area will become bigger. Okay, the area will become bigger if the E2 is less than E1, and then the area after transformation will become smaller. Alright, so this is the illustration how the transformation, how we do the transformation from the composite beam, okay, composite beam, okay, into equivalent homogeneous beam, okay, equivalent homogeneous beam. Okay, so let's say for this case, okay, let's say E2, okay, Young modulus for material 2 is bigger than Young modulus of material 1. So after transformation, so if we transform material 2 into material 1, so after transformation, the area of the material 1 will become bigger. Okay, become bigger. Where the width, okay, the original width of the material 2, which is B, must be multiplied by the transformation factor n. So the width, okay, after transformation become NB. Okay, or we also can transform material 1 into material 2. Okay, material 1 into material 2, because the E1 is less than E2, so after transformation, the area for the material 1, okay, the transform area of the material 1 become smaller, okay, smaller, and the width, okay, same thing, the original width is B, so after transformation, so the width become NB, okay, NB, okay. Why the width becomes smaller? Because the n, okay, the n is less than 1, okay, less than 1. All right, let's look at for the next slide. Okay, so what is the n? So we recall back. So if you recall, the n is equal to E2 over E1. If you want to transform the material 2 into material 1, and or n equal to E1 over 2 if you want to transform material 1 into material 2. Okay, so after the transformation, okay, we can calculate the stress in the beam for each material, where the stress for this case, if we transform material 2 into material 1, okay, so 2 into 1, so the stress 1 equal to my over I, and sigma 1 equal to my over I, and sigma 2 equal to n multiplied by my over I. Okay, so this is the summary. This is the explanation. Okay, if the area was not transformed, okay, so the area not transformed, then simply calculate the associated bending stress from the factorial formula. So the area that we are not transformed, okay, the stress is equal to my over I. Okay, if the area was transformed, if we transform the material that we transform, the stress is n my over I. K over I minus. Okay, so that's the material without transformation. This is the material with transformation. Okay, thank you.